Okay, thermodynamics is a branch of science which deals with the study of different forms of energy and their interconversion. Adiabatic expansion of ideal gas. When expansion of ideal gas is carried out at constant heat such that no other heat can enter or leave the system, then it is called adiabatic expansion of an ideal gas. Deduction of TB relation from the first law of thermodynamics, dq equal to d plus pdv. For adiabatic process, dq equal to 0. Cv equal to d over dt, so d equal to cv dt. For 1 mole of an ideal gas, pv equal to RT, so p equal to RT over v. Now putting the value of d, dq and p from the equation 2, 3 and 4 in equation 1 we get dv over v equal to minus cv over RT dt. When temperature is changed from T1 to T2, then volume of ideal gas is changed from V1 to V2. For approximate calculation, Cv is assumed to be independent of temperature. Integrating the equation 5, we get V2 to V1, dV over V equal to minus Cv over R, T2 over T1, dt over T. ln V2 over V1 equal to Cv over R, ln T1 over T2, equation 7. Equation 7 can be written as ln V2 over V1 equal to Cv over Cp minus Cv, ln T1 over T2. And solving, we get Cp over Cv minus 1, ln V2 over V1 equal to ln T1 over T2. So gamma is the Cp over Cv, where gamma minus 1, ln B2 over V1 equal to ln T1 over T2, and where gamma is called molar heat ratio, gamma equal 1.66 for monoatomic gas, gamma equal 1.44 for diatomic gas, gamma equal 1.30 for triatomic gases. Above equation 8 can be expressed as ln B2 over V1, gamma minus 1 equal to ln T1 over T2. Taking antilog on both sides, B2 over V1, gamma minus 1 equal to T1 over T2. T1 V1 gamma minus 1 equal to T2 V2 gamma minus 1. So TV gamma minus 1 equal to constant. Again from equation 7, ln B2 over V1 equal to ln T1 over T2, Cv over R. We also know that x ln y equal to ln y on x. Taking antilog to the both sides, B2 over V1 equal to T1 over T2, Cv over R. So V1 T1, Cv over R equal to V2 T2 Cv over R. Taking R over Cv power to the both sides, we get Tb gamma minus 1 equal to constant. Deduction of PV relation, we know that T1 V1 gamma minus 1 equal to T2 V2 gamma minus 1. For ideal gas, PV equal to RT, so T equal to PV over R, T1 equal to P1 V1 over R, and T2 equal to P2 V2 over R. Substituting the value of T1 and T2 in 1, we get P1 V1 gamma equal to P2 V2 gamma, PV gamma constant. This is the pressure volume relation in adiabatic change. Reduction of TP relation, we know that P1 V1 gamma equal to P2 V2 gamma. For ideal gas, PV equal to RT, so V equal to RT over P, V1 equal to RT1, P1 and V2 equal to RT2, P2. Now above expression can be expressed as P1 RT1 P1 gamma equal to P2 RT2 P2 gamma. So we get T gamma P1 minus gamma constant. Thermodynamic processes are the parts we can take to bring our thermodynamic system from its initial state to final state. Isothermal process iso same thermal temperature. The thermodynamic process which is carried out at constant temperature is called isothermal process. This process can be achieved by keeping the process in thermostat for isothermal dt equal to 0. Isobaric process iso same value of pressure. The thermodynamic process which is carried out at the constant pressure is called isobaric process, dP equal to 0. Isochoric process, the thermodynamic process in which volume is constant, is called isochoric process. For example, a system is heated in a non-expanding chamber, dV equal to 0. Cyclic process, when a thermodynamic process is carried out through a series of steps and ultimately brought to the same initial state, then the thermodynamic process is called cyclic process, Carnot cycle delta equal to 0. Adiabatic process, the thermodynamic process in which no heat can flow into or out of the system, is called adiabatic process, dq equal to 0. For example, this process can be achieved in an insulated container such as thermos flask. Isoenthalpic process, the thermodynamic process in which enthalpy of the system is kept constant, is called isoenthalpic process. Delta S equal to 0, Joule-Thomson experiment. Work done in adiabatic reversible expansion, W reversible. Let us consider an ideal gas having the volume B at pressure P and temperature T. If the ideal gas is allowed to expand reversibly, maximum work is obtained. Since the process is adiabatic, no heat enters or leaves the system. Hence, work done in the compensation of the internal energy of the ideal gas and temperature of the gas decreases accordingly. The pressure-volume relation under adiabatic conditions can be graphically shown as in the adjoining figure. For infinitesimal change in the volume dV at the corresponding external pressure P, the work done is given by the shaded area ABCD in above figure. Mathematically, the work done is given by dW equal to PdV for adiabatic process, PV gamma equal to K. So P equal to K over V gamma. Now putting the value of P in equation first, dW equal to K over V gamma dV. When the ideal gas expands adiabatically and reversibly from initial volume V1 to final volume V2, then the total work done by the gas is equal to the PV area ABCD in the above graph. Here the total work done is obtained by integrating equation 3. So integrating V1 to V2 dW, K V1 to V2 dV over V gamma, and solving we get V1 to V2 dW equal to 1 over 1 minus gamma, Kb to 1 minus gamma minus Kb1 1 minus gamma. We know that K equal to P1 V1 gamma and equal to P2 V2 gamma. So substituting the value of K in above equation and solving, we get 1 over 1 minus gamma P2 V2 minus P1 V1. We know that PV equal to nRT. And again, nR over 1 minus gamma T2 minus T1. And the value of gamma is always greater than 1. So W reversible equal to nR over 1 minus gamma T2 minus T1. If T1 is greater than T2, positive work done by system and temperature decreases. If T1 is less than T2, negative work done on system. Adiabatic irreversible expansion, W irreversible. Let us consider a gas expand irreversibly from volume V1 to V2 by decrease in external pressure from P1 to P2, then irreversible work done by the system. W irreversible equal to P2, V2 minus V1 from ideal gas equation, V1 equal to nRT1 over P1 and V2 equal to nRT2 over P2. Substituting value of P1 and P2 in equation we get, and solving nR T2 minus T1 over P1 P2, W irreversible equal to nR T2 minus T1 over P1 P2. Using the first law of thermodynamics process, W irreversible equal to minus delta E equal to minus NCV T2 minus T1. From equation 2 and 3, R n is common, and solving we get T2 equal to T1 Cv or T2 over P1 over Cp. Thus, by knowing the value of T2 from the equation 4, work done by the system during the irreversible adiabatic expansion can be calculated by using equation 2. Joule-Thomson effect, it is the phenomenon of lowering of temperature when a gas is expanded adiabatically from a region of higher pressure to the region of lower. This effect stated when the real gas are allowed to pass adiabatically through a porous plug from a region of higher pressure to a region of lower pressure, there is a sudden drop in the temperature. Schematic representation of Joule-Thomson experiment. Mathematically, formula of Joule-Thomson effect, let P1 greater than P2, the work done by a piston A on gas equal to minus P1 B1. Similarly, the work done by a gas on the piston B, P2 B2. Then total work done, W equal to minus P1 B1 plus P2 B2. According to the first law of thermodynamics, Q equal to delta E plus W. Since gas expands adiabatically, delta E plus W equal to 0, delta E equal to minus W. Comparing the equation 1 and 2, we get from the equation and definition of enthalpy, H equal to E plus PB. So E2 plus P2 B2, S2 and E1 plus P1 B1, H1. So S2 equal to S1, S2 minus S1 equal to 0. So delta H is 0, dH equal to 0. Thus, it leads to the conclusion that when the expansion of a gas takes adiabatically through a porous plug, the enthalpy of the system remains constant. Thus, adiabatic expansion of a real gas occurs not with the constant internal energy, but with constant enthalpy. Joule-Thomson coefficient, let us consider enthalpy as is a function of temperature and pressure, H equal to FPT. Applying the Euler's theorem, we get dH equal to delta S over delta P, T dP plus delta S over delta T P dt. Since Cp equal to delta S over delta Tp, so equation 2 becomes dH equal to delta S over delta P, T dP plus Cp dt. For the Joule-Thomson expansion, dH equal to 0. So above equation becomes delta S over delta P, T dP plus Cp dt equal to 0. So Cp dt equal to minus delta S over delta P T dP. So dt over dP equal to minus 1 over Cp delta S over delta Pt. The variation of temperature with pressure at constant enthalpy is called Joule-Thomson coefficient and denoted by mu. So mu equal to minus 1 over Cp delta S over delta Pt, where mu is the Joule-Thomson coefficient. The Joule-Thomson coefficient is defined as the rate of change of temperature with respect to pressure at constant enthalpy. Condition significance, we know that mu equal to minus 1 over Cp delta S or delta Pt from Joule-Thomson coefficient. If mu equal to 0, inversion temperature, no cooling, no heating, there is no Joule-Thomson effect. If mu equal to positive, gas shows cooling effect. If mu equal to negative, the gas shows heating effect. Inversion temperature, we know that mu equal to minus 1 over Cp delta S or delta Pt from Joule-Thomson coefficient. Every gas has definite temperature and particular pressure at which the temperature at mu equal to 0, that is the gas neither cooled down nor heated up on the adiabatic expansion, is called inversion temperature. Spontaneous and non-spontaneous, the process which proceeds by themselves without any external additional effect are called spontaneous process. All natural processes are spontaneous process. Example, melting of ice at room temperature. The processes which are not processed without any external additional efforts are called non-spontaneous or unnatural process. Example, to stop ice from melting requires additional efforts. Second law of thermodynamics statement, the thermodynamics state quantity that measures the randomness or disorderliness of the molecule system is called entropy. Kelvin Planck's statement of second law of thermodynamics, it is impossible to construct an engine which is operating in a complete cycle, will absorb heat from the single body and convert it completely to work without leaving the change in the working system. Cauchy's statement, it is impossible for a self-acting machine unaided by an external agency to convey a heat from the body to a lower to another at a higher temperature. That is, the heat cannot pass itself from the colder to hot body. Planck's statement, it is impossible to construct a machine operating in cycles that will convert heat into work without producing any other change in the surroundings. Entropy is denoted by the symbol S, and more is the randomness of the system, more is the entropy. For example, if we heat any object, the velocity of molecules increases and hence the disorderliness also increases. It means that entropy of the substance increases. If the system absorbs Q amount of heat at a temperature T, and the increase in entropy of the system is given by delta S equal to Q over T. If system absorbs Q amount of heat, Q will be positive. Entropy change will also positive. Positive delta S indicates that entropy of system increases. Delta S system equal to dQ reversible over T. Heat absorbed by the system is taken as positive. If the system lost Q amount of heat, Q will be negative. Negative delta S indicates that entropy of the system decreases. Delta S surrounding equal to minus dQ over reversible over T. Heat lost by the surrounding is taken as negative. So delta S universe equal to delta S surrounding plus delta S system equal to dQ reversible over T plus minus dQ reversible over T equal to 0. All spontaneous processes are accompanied by increase in entropy work done by the system. W irreversible is less than W reversible.